Okay, in this video I want to explain L values and R values and what the differences are. It may seem a bit unnecessary for us to go and explain all of this stuff, but it's important terminology that you need to know. So when you go and do debugging in Visual Studio, for example, you'll often see the terms L value and R value. And also when you look at other tutorials, maybe online, so it's kind of important to know this. And then also for some of the other things. So when we talk about dynamic memory and so on, it's important to know what an object is as well, for example, and basically the difference between that and a variable. Now, an object is essentially data in some block of memory, just the data, whereas a variable is an object with an identifier. So typically we use the identifier as if it is the object itself. You declare some integer x and you set that to 5. The value 5 is stored in memory, and x is the variable identifier used to declare the object. If you want to read to or write from memory, then you simply use x, you simply use that variable name, and then you can do x plus 7, which will be the same as 5 plus 7, right? So again, we can simply use the variable name or identifier as if it is that object itself, the value 5 that is stored at some memory address. Now what's important to note from this is that not all objects have identifiers. Dynamic variables, for example, do not have identifiers. You just have the object that lives at some memory address, and we'll have to use some pointer to manage those types of objects. And if you don't have some pointer to that address in memory where that object is located, then essentially you cannot access that object. So we'll discuss this in more detail later when we talk about dynamic variables. Next, I want to talk about what an L value is. So an L value is an expression that evaluates to the address of an object in memory. An example is a variable, including const variables, dereference pointer. Of course, to dereference a pointer that must have some valid address. You can't dereference a null pointer, for example. Array elements, those also have an address in memory, as we've seen. Class members, or a function or a conditional operator that returns an L value, maybe a pointer to a dynamic variable in memory, as we'll explain later. So an L value is basically short for left-hand value or left value, sometimes also referred to as locator values. And this is typically some variable name or some operand that you'll find on the left-hand side of the assignment operator. In other words, when we assign something to that L value, either a literal, which is actually an R value, and we'll talk about that shortly, or some value stored in another variable or some other address in memory, so from an array or something like that. Now, the left operand in an assignment statement must be an L value. In other words, it needs to be some expression that evaluates to an address in memory. You cannot assign something, or in other words, store some value nowhere, right? You need to store it in an address in memory. Here are a few quick examples. Int x is equal to 12. X is an L value. So we are declaring and initializing x. Now, after this statement, I can do x is equal to 15, for example, and change x. You cannot assign x to 97. So that's an incorrect usage. The left operand must be an L value, right? It needs to have some address in memory, basically. And then we have the R values. Now, an expression that does not evaluate to the address of an object in memory is an R value. You can think of this as the right-hand value. So typically the expression on the right-hand side of the assignment operator that is used to initialize a variable, for example, one L value. So an example here is a literal or an expression that evaluates to a literal. It can also be a literal returned by a function call. So here's an example. 12 is an R value, where declare x and initialize it to 12. 12 is going to be an R value. And then when you assign x plus 8 to y, when you declare y, x plus 8 is going to be an R value. That is going to evaluate 8 plus 12, which is going to be 20, right? That's going to be a literal. And then you assign that literal value, which is going to be then an R value, to y. So in x plus 8, x is of course an L value, but in this context, it's used as an R value because it's going to evaluate, it's going to fetch that value in memory, essentially, and then it's going to become an R value. Okay, so I have a quick demo. I have integer x, I set that to 5, so x is an L value, it has an address in memory, and then 5 is just a literal, so that is an R value. Then I do int, and I do x ref, so a reference to that integer. I initialize that to x, and then I go and change that to 50, and then I print it out. Xref should now give us 50. Okay, but what if I try and do something else? I have this reference here, which I'll just call ref, and I try and set that to 55. If I hover over the squiggly line, the information that it provides us is initial value of reference to non-const must be an L value. You'll get some weird error, cannot convert from int to int reference, but really what it's about is that this is literal, and of course we can only assign an L value to a reference. Alright, so actually one more demo on this. Since y is an L value, we can assign an R value to that, but let's say we do x plus 3. So when it initializes y, in this case, it's going to fetch whatever is stored in x, which is going to be 5. So it's going to do this calculation. It is going to return an R value, which you then store in y. But let's say I try and do something like this. So we do x plus 3 is equal to 5. That doesn't make any sense. Expression must be a modifiable L value. So this section on the left doesn't return a variable, essentially, that we can assign to. It just does some calculation. This will give us 8. Cannot assign 5 to 8. Same thing with this. We want to assign x to 3. That doesn't make any sense, right? Because 3 is just a literal. So far in the course, the values that we return from functions are typically integers or floats, and those are not L values, those are just R values that get returned. So we don't actually return something from the function with a memory address, right? So in the next section, I'll talk about how we can return a reference from a function. Typically, local variables that go out of scope will get destroyed. Once we are done executing the function and we return to the parent function, the local variables get destroyed. That includes all local variables that you create in the body of the function and also whatever variables you pass in by value as opposed to passing by reference. But to return a reference to something, you want a local variable that you don't destroy or that persists or stays in memory after the function finishes execution. So what we can do is we can create static variables in that case. So in this section we'll focus primarily on local static variables in functions because you have static functions. You have static members, so within classes, for example, or structs, and so on, and we'll discuss those later on. So for right now, once again, we are mainly concerned with static variables as you would use them in functions. Now we can declare a variable as static simply using the static keyword, as you see in the demo right below here. So I have static int current game level, for example, and I set that to 1. Now the memory that is allocated for the object or variable persists for the duration of program execution. Memory is deallocated when the program ends or terminates. That object is going to stay in memory even after you are done executing the function. Memory allocation and initialization occurs only once, the first time the function executes, of course, and the value of the variable will carry over to each successive function call. So let's say you increment the value in that function each time you call the function, then it's not going to redeclare and reinitialize that static variable each time. It's only going to do the declaration and initialization once, and then from there on, each time you call the function or make a change to that variable, then it's going to reflect in that variable. So with this, I'll move over to Visual Studio and we'll look at a quick demo. Okay, in this section, I want to show you how you can return a reference from a function. So some reference to an integer that you create in a function, for example. So I'll just go and create a function. Maybe call it getInt. Let's say we want to return a reference, then we can change this here. This really is the type that is going to return, right? We want to return a reference to an integer. Currently this is not very useful because the integer is local, and essentially once we are done executing the function and we return to the parent function or to the caller, then this integer variable will go out of scope. So even though we return some reference, we are going to lose the variable, right? The variable is essentially going to get destroyed. It's not very useful in this case, so what we can do instead is we can create a static integer called temp, and then we can return that. So this is going to exist for the duration of the program. So essentially this function now returns an L value because what it returns, this integer here, will have an address in memory. So what's really weird with this is we can do I'll do console output and we should get 50 now. Or we can add 50 to that, something like this. We should get 60 now. The syntax is really weird. We now have a function call on the left. Now the functions that we've written so far that we've seen throughout the rest of the course typically returned either an integer or a float, for example, and so on. So the basic types. That is why this syntax here, this statement, seems a bit weird. Because what's going to happen is those functions that return just an integer or a float, for example, will return an R value, and you cannot assign to an R value. You'll get an error. But in this case, we are not returning an R value, we are returning an L value, because we are returning a reference to this integer called temp, which will remain in memory even after this function call has ended. So we return a reference to that, and if this is a bit too weird, what you can do is something like that. We can go and get whatever this function will return, so it will return 10. But if you want to change it, of course, let's say we want to change x now, it's not going to change temp, it's only going to change x. Unless you go and create x as a reference as well, and we do x like this, and then we do getInt, and you can see that it works just fine. So this is an alias for whatever this returns, which is also going to be an alias for this variable, essentially. Just for fun, let's go and increment this each time just to see what happens. So each time we call the function, it's going to increment temp. I'll do a pointer. It'll return some reference. We don't see it, but it's right here. So from that reference that we get back, let's assume once this calculates, it returns some variable. Let's say that variable is x, okay? And it is a reference to this temp here. So what we want to do is we want to get the address of that in memory, because we want to assign that address to this pointer. Then here we go and dereference that pointer, and we assign 500 to that. Or actually, let's go and add 500. Add 500, so we should get 510. It will actually increment that, so 511. And then here we print it out again. We should get 512. You can see that is what we get. So don't worry too much if you don't get what's going on here. Maybe revise what a reference is, what a pointer is, and just take it step by step. Now you won't be using this here all that much, so returning a reference to something from a function. You'll also see the static keyword being used in classes, which are similar to structs. You'll see them being used with functions and so on, and we'll discuss that, the details around that in future videos. So I just wanted to introduce the static variable in this section, and then also the fact that you often get weird looking statements such as this one, and as a beginner this may look really complicated, but what you need to remember is just take it step by step. If you see something like this to the left of the assignment operator, just go and look at the implementation. It'll either return some reference or a pointer depending on what's going on here and so on. And in fact, if you hover over this, the LPS shows us it'll return a reference to some integer. So essentially this is an L value, and we are assigning some R value to that. So it's not that difficult if you just take it step by step. Go and look maybe at the implementation, or here hover over this and read what the helper gives us, okay, what the IntelliSense gives us. Right, I hope you found this section interesting. At least for the most part, we won't be doing stuff like this. For the most part, we'll be returning pointers to dynamic memory and so on. But I hope this was interesting at least, and that it helps clarify again the difference between L values and R values. Now we've talked about parameters and references, so passing by reference and so on in the previous lectures. We also have something called R value references. Now this is useful for move constructors and move semantics. We'll talk about that in more detail in future lessons, but I want to introduce the basic concept here since we are talking about R values and L values in this lecture. So firstly, I have the L value reference, which of course is references to L values. So you have an example, int p, set that to 5, and then I simply do a reference to that. So that is an L value reference. So we assign p to that. Now an R value reference will reference R values or temporary objects. Of course, if you have some literal such as 5, or let's say you do 5 plus 5, and that returns some R value, so 10. That basically is a temporary object, right? It exists somewhere. It's not a variable, it's just a temporary object. Now you can actually create a reference to those temporary objects. And this is useful because if you have constant references, so informal parameters right in a function, then you cannot make changes to what you pass in. Now in that case we can pass in literals because the compiler will essentially create a constant variable behind the scenes and then assign that literal to that. But we cannot change it in the body of the function because it's qualified as const. So that is one place where R value references come in handy. Now the operator that we use for this is two of those ampersand characters, so double ampersand. And as we'll see in later examples, we can overload our functions and then the compiler will deduce which function to use based on the argument that we provide. So in the function that we overload, let's say in one declaration, we have an L value reference, and in the next one we have the R value reference. Those are different, they won't be seen as the same thing, and so of course that means we can overload functions in that way. And depending on what we pass in, the compiler will deduce which function overload to use. Okay, so if you pass in a variable, then it's going to use the L value reference. If you pass in an R value, such as a literal 5 for example, then it will use the overload with the R value reference. Just a few examples on R value references. With the L value reference, I only use a single ampersand. Now the spacing here is a bit weird just to highlight the fact that I use a single ampersand here. And the same with the R value reference that we'll talk about here in just a second, and which will be the next statement. But this is just white space, so the compiler is not going to care about, where those ampersands go. And I'm trying to initialize the L value reference to 100. As I discussed in the lecture on references, this will give us an error. That 100 literal is a value that will exist temporarily somewhere in a register, but it's not going to be stored the same way that a variable is stored, right? So you cannot reference that using an L value reference. Now that being said, in the next statement, we have an R value reference, and this will compile. With an R value reference, again we use the double ampersand, and I can initialize that to the literal 5 and that will work fine. In the final two statements on the slide, I have an integer p, which I'll set to 97. Then if I declare some R value reference, let's call it q R value ref, you can see I use the double ampersand there, and I try and initialize that to q, we will get an error if we try and do that. So this can only reference a temporary value, such as 5 or something like that. Okay, so I'll open up Visual Studio and we'll look at a few demonstrations on this. I have this function, print score, and it currently has an L value reference. Down here I use it, I just pass it a variable, and then it will print it out in the function. Build and run that, and that will print out 75, or whatever you initialize this variable to. Now we can always go and change this. And maybe I'll print it out down here as well. This can be a bit confusing, so I'll actually just change this parameter here to x so that it is not the same as the variable. So I'm printing out score, and then we do the function, and in the function I change x, which is actually now a reference or an alias for score. Alright, let's just print that out, and you'll see we get 75. In the function we change it, and then we print out 97. Now if I change that to a constant, because let's say I want to go and pass in instead of this here, so I'll comment those out. Let's say I want to pass in something like 7. Now this will work fine, apart from the fact that I want to change it in here. Of course, if I remove the const, then it's fine, I can go and change it. But if I try and build and run, we'll actually get an error. And that's because what we pass in here must be an L value. This is an L value reference, so it expects a variable, right? So this will work with const, but we'll get an error over here because we're trying to change it. I'll just comment that out, and this will work fine now. Okay, so what I'll do is I'll overload this function, and then I'll go and change this here. Just remove that. So here I have a R value reference, and then up here I have a constant L value reference. Okay, I'll just comment this print score function with the L value reference. I'll go and comment that out. This one with the R value reference will now work fine, so I'm passing the literal as an argument to the print score function. Build and run that, and you'll see we get 7 printed out. We can even change this, and that works fine. Let's say I go and pass score in here. We get squigglies. You'll see an R value reference cannot be bound to an L value, right? So if I build and run that, again, we'll get an error. You cannot bind an L value to an R value reference. So that is basically what we need to keep in mind. I'll just uncomment that. Just remove that line. I'm not going to change the formal parameter x in this function. I'm not going to change. So I'm just going to keep it at const. And then if we pass the score in here, so the variable score is an L value. And because of that, the compiler will deduce which function overload to use. And in this example, it's going to use this one here with the L value reference. Build and run that. And you'll see that works fine. Can actually remove that. If we add some literal in here, 88 for example, that'll get passed in here, of course, and it's gonna get changed, and then it'll print it out again. Build and run that, and you'll see what I mean. So personally, I don't use this all that much, but it can be handy, and it's really in this step of something called move semantics and move constructors and so forth, and we'll discuss that in the object-oriented programming sections. Although we've already talked about object-oriented programming to a certain extent in the structs lectures, but we'll go into much more detail in the upcoming lessons on that. And I felt like it was important to add here, so it's kind of out of the way, and it is part of this L value and R value lecture. So I hope you found this useful, and I'll see you in the next video.